Let's do number 2. Let f and g be the functions defined by f of x and g of x. This is calculator active. It is impossible to do without some sort of technology. So let R and S be the two regions enclosed by the graphs of f and g shown in the figure above. Find the sum of the areas of regions R and S. Okay, so here's the thing. If I want to find the sum of the areas of these two regions, then I need to add this region plus this region. And I'm going to go back to another lesson that we have done. And it is basically top function minus bottom function. So the integral of the top minus the integral of the bottom. Top minus bottom. Don't make it harder than it is. But now the thing is, I don't know which one's on the top and which one's on the bottom. So let's graph. This is calculator active, lucky us. And so we're going to graph them both. I still have my functions left over from the last problem. Oh, by the way, we're going to graph it from 0 to 2 on the x-axis. So here goes. 1 plus x plus e to the x squared minus 2x. We'll clear that out and we'll have x to the 4th minus 6.5x squared plus 6x plus 2. And we're going to graph it from 0 to 2. And when you do that, you can also press zoom fit, which is zoom 0, and that will automatically take it to the right y values that will just really show you the features of the graph that you need to see. There we go. Okay, so when we graphed this, on my calculator, the blue one is y, and y1, the first one, and the red one is y2. So that was f, that was g, and so I'm not sure how well the colors are showing up on your screen, but basically, here's the thing. You can graph them separately if this doesn't make sense. If I'm going to do that area plus that area, I need to know which one's where, which one's on top, which one's on bottom. So which function is greater than the other one? So let's go ahead and start number 2, part A. Number 2, part A. We want to find the sum of the areas, regions R and S. Well, that's going to be this minus this. So the integral from 0 to O, I don't know where that is. We'll come back to that. Of this function minus this function. Okay, well, for me, it's red minus blue. And that would be g minus f. And I don't have to write all that function again. I'm just going to write g, and then what did I write? I wrote an f. g minus f dx, and then we're going to add it to find this area right here, and it's going to pick up where the other one left off, so whatever that is going to go there, and then we're going to do top minus bottom. Well, again, in this case, that's going to be blue minus red, and blue, for my calculator, was the first function, the f function, so this is going to be f of x minus g of x dx, and it's going to end at 2. So now we kind of have this dilemma where we need to find out exactly where this is, find out exactly where they meet. So let's go to the calculator. We're going to press graph again. I need to know exactly where that is. It is not safe to assume that it is 1. I'll go ahead and tell you actually it is not. So second and calc, and we want to find where they intersect. That's number 5. Enter, enter, enter. And I have 1.032839. I want this to be as accurate as possible. So they intersect at 1.032839, comma 2.40. I don't really care about the y values. That's not really relevant. But I'm going to store that as a in my calculator, or whatever you want to store it as. Don't store it as anything crazy like x or y. Don't do that kind of stuff. But we will store it as something. Right now in my calculator, it is x. So I'm going to escape from there. I'm going to press x. And I'm going to press STO. I want to store it as, well, I've defined it as A. So now I have that as A. Before I do anything else, I need to do that. Because if I was to graph again, then I may not have the same, well, I would, never mind. I may not have the same X value if I would have graphed again. Like if I'd have added another graph and it was going to have to do that, then it would mess up what my X was stored as. I need it to be something other than X. Anyway, we have A, and for the people that are grading my AP test, they know when they see, oh, A, what's A? Oh, there it is. I have it, and I have lots of decimals because I want the whole thing as accurate as I can. I know I've said 3 decimal places, but as I do this, I'm going to be using as many decimal places as I can for accuracy. And the calculator has it all stored in there. So now we're just going to type that in. So math 9, we're going to go from 0 to a of g, that's y2. Don't lose track of which one's which, minus y1. There we go. By the way, I do want to point out, don't lose track of which one's which, because if they give you G first, then F, you could easily mix them up, and it's very easy to do. It'll give you some opposite signs, but you can run into a lot of problems with that. Excuse me. And we're going to go from A to 2, and we'll do F minus G dx. There we go. And 2.004 is my answer. We have found the sum of those 2 regions. Okay, we've done part A, and so now let's move on to part B. The region S is the base of a solid whose cross-sections perpendicular to the x-axis are squares. Find the volume of the solid. Whoa, 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 slow down there. Okay. So far, everything we've done is one-dimensional. I'm sorry, two-dimensional, not one-dimensional. It's not a line. It's two-dimensional. It's on a flat plane. It fits on this piece of paper. What's about to happen, though, is we're going to take this piece of paper and we're going to expand it up, and we're going to build a little building right here. And the building is going to fit right here in region S. What's this building going to look like? Well, S is the base of a solid whose cross sections perpendicular to the x-axis. Don't ever think it. It means it's just sitting like this. It's not sitting like this. It's sitting like that. Perpendicular to the x-axis are squares. So I have squares, and they're going to be sitting like this. Now this one's clearly too big, because what it means is I'm going to take this region S, and that distance right there is the base of a square, so it's going to come up that same distance. So when I raise this building up, it's going to go up, back down, up, over, back down, up, over, back down. Over here where the distance isn't much, it's not going to go up, over. It's going to go up, over, down. It's going to be shorter. Okay, don't overthink this. An integral adds together lots of other numbers. Let me reword that. When I was finding this, and please don't ever think what I'm about to say. When I was finding these areas, what I was really doing was, like way back in the day in a different chapter, we were basically adding lots of super skinny rectangles here. That's essentially what we're doing. But now for part B, I'm not adding a bunch of super skinny rectangles. I'm adding together a whole bunch of squares. What's the formula for the area of a square? Well, it's length times width where they're equal to each other. So it's the length of the side squared. What's about to happen here is, well, this is the formula for the area of a square. Okay, the formula for the area of a square is going to go from here to here. That's A, capital A, to 2. So A to 2, dx here. And then the top one was F for that region. The bottom one was G. So here's what just happened. The distance between here and here is F minus G. And if I take that distance and I square it, then I have just formed, well, a square. So the distance squared gives me a square. And my integral is going to take all these little squares, add up all their areas, and it's going to give me the volume of something. So now I'll type it in my calculator. So math 9 from A to 2 of, now I can't squeeze the squared outside of the automatic parentheses, so I'll have to do it like this. So y1 minus y2, we'll square that, dx, 1.283. Now what does that represent? We have just built a building. I know I'm taking a while with this, but I want to make sure we understand it. We've just built a building where this is the floor plan. This is the bottom of it. And it comes up and it makes a square that is equivalent to the same distance here, perpendicular to the x-axis, as the floor plan. What is the volume of that building? 1.283 cubic units. That's what that is. All right, let's do part C. When I first read part C, well, I'll tell you what went through my head when I read it. Let h be the vertical distance between the graphs of f and g in region S. Okay, still dealing with that. Find the rate at which h changes with respect to x when x equals 1.8. That sounds like related rates to me. So it is related rates, but it's not related rates. Like once we get into it, we'll realize that we didn't have to go through that whole process. But I'm going to start writing down stuff that makes sense in terms of related rates. So, reading the problem again, h is the vertical distance from here to here. All right. Find the rate at which h changes with respect to x. Okay, so they're basically saying find dh dx when x is 1.8. Okay, fine. Well, with all related rates problems, you need at least one formula. So what is h? Well, h is the vertical distance between f and g, and it is f minus g because we're in region S. Again, that's f, that's g. If we were over here, it'd be g minus f. Okay, just throwing that out there. Okay, so let's take the derivative, and you might get all crazy with it and be like, well, I got to take the derivative of this with respect to that, and yeah, you do. But we're taking the derivative with respect to x. So the derivative of h of x with respect to x is, you could call it dh dx if you want to. I'm going to call it h prime, right? I mean, don't make it harder than it is. And then the derivative of f, that's f prime. And the derivative of g, that's g prime. So we get in this habit of dh dt, df dt, dg dt. This isn't t, this is a, x. Pointed at the x and said a. I want to know what happens at 1.8. Okay, fine. So h prime of 1.8 is equal to f prime of 1.8 minus g prime of 1.8. Well, now I have to take a derivative here and here. And now I have to take a derivative of that and of that. Oh no, I have to do all that work. No, you don't. It's calculator active, so don't. Lucky us, we got what we need right here. Math, not 9, 8. So I want to take the derivative with respect to x of my f function, so y1, and x equals where? Well, 1.8. There we go. That's going to give me this little piece. Minus math 8 again. The derivative with respect to x of my g function at 1.8. Negative 3.812. There we go. Okay, what I have failed to do as we go through this is tell you how they score it. So I'm going to kind of show you the answer key in conjunction with what I've written so far. So here goes. For part A, you get 4 points. Let's go from the end first. You get a point for the answer. You get a point for this and this all together, like those numbers right there. They call them the limits. Don't think of limits like the limit as x approaches. It's just, the numbers on your integral sign. And then your integrands, which would be these little guys right here. So like this and this. I don't know if it was automatically like 2 points or like a point here and a point here. I don't know how that worked. I don't know if it was like you get both points or you get nothing or you get one or the other. I don't know. Anyway, here's 4 points. There's one. There's one, there's one, and there's one. So there's 4 points. Part B, you get 2 points for this. So that, and then I'll underline it. You get 2 points. There you go. And then final answer is that. And notice there were no points that came along with that. You just had to have it right to get the answer. All right. Part C. Final answer is a point, and then h prime, you had to kind of know what h prime was, and that would be this right here. So you had to consider that.